Hello and welcome to today's video. In today's video we're going to be going over how to find the area in between curves. So to start out, let's ask ourselves a question, or let's just take a step back. How did we find the area of a single curve? And that was by adding up a ton of tiny rectangles. So what we're going to do now is we're going to apply the same philosophy to find the area between curves. And then we're going to try and find a formula for this. So let's say I want to find the area between the point A and point B between the curves g of x and f of x. Well, what you have to do is you'll have to sum up a ton of rectangles. And let's just take a moment and ask ourselves, what is going to be the true height of these rectangles? Alright, what's going to be this h value here? Well, we know that each of these rectangles have a height of g of x, but they also have a bit more added on by f of x. Or I suppose I should probably do that in a different color to show it a bit more. So it's going to be, and now let's look at another spot. I think it becomes a bit clearer then. Well, we have our area of g of x, or our height of g of x, but it's also minus this height of, this height of f of x minus this height of g of x. So we really get that this is going to be the sum from I is equal to 1 to n of f of x, a height f of x, minus the height of g of x, and multiply that by the change of x. Now this is just an approximation, so if we want to get the exact area, we can now take the limit as n goes to infinity. Now I kind of just want to break this down a small bit here, so let's just call this function here let's call this h of x. So because we can see that this is going to be really the limit as n goes to infinity of the sum from I is equal to 1 to n of f of x of I, or in this case, h of x of I, since we defined this new function, multiplied by the change in x, we know that this is just the definition of a definite integral. So this is going to be the integral from a to b of h of x of I. Just h of x. And then multiplied by dx. Now what we're going to do is we're going to just sub in our original h of x, and we'll see that we'll get this expression for the integral from a to b of f of x minus g of x times by our dx. Not changing xd. Alright, there we go. So now if we want to apply this to our world of mathematics, we're often going to be asked to find the area enclosed by a curve. So we are going to be given two curves. We're going to have to solve for where they're equal to each other, and then we will use those points to then find a solution. So let's real quickly just sketch out a graph of what cosine of x and e to the x look like. Well, we know e to the x at 0 is equal to 1, and then cosine at 0 is also equal to 1. So this is going to look something like this. Well, now what this curve or cosine is going to be doing is it's going to be oscillating here. But this e to the x, which I haven't actually sketched in yet, and I suppose I might want to do this in a different color, is going to do something on the lines of this. So we want to know what areas in between these two curves, which intersect at the point 0, or x is equal to 0, and then x is equal to pi over 2, which I'm just going to say is going to be right here. So what we're going to do is we're going to take this integral from their point of intersection, which is 0, to the ending point, which would be pi over 2. We know our top curve, which remember that we normally want f of x up here to be greater than g of x for all x in the domain, but that's not always true. Sometimes you can get away with not. So what we're going to do is we're going to take this integral from 0 to pi over 2 of e to the x minus cosine of x dx. Evaluating this integral, we get the integral from 0 to pi over 2. Or let's actually just evaluate this. So we get e to the x minus sine of x evaluated at pi over 2 and 0. So evaluating at pi over 2, we get e to the pi over 2 minus sine of pi over 2. Sine of pi over 2 is actually 1. Minus now e to the 0 minus sine of 0, which is 1. Wait. Yeah, sorry, sine of 0 is 0. Apparently I don't know my trig. So we get e to the pi over 2 minus 1 minus 1, so we get e to the pi over 2 minus 2. Alright, so now we want to find the area enclosed by the following curves. So what we do is we're going to start by sketching a graph. I think that's always helpful. So we're going to figure out what's the equation for this parabola, and I think we can all see that this is going to be an equation or a parabola with with zeros at 0 and then 4, and it's going to open up. I don't really care about much more detail than that. Then we have the line that's equal, y is equal to 2x, so that's going to come in here like something like that. I don't know where it's actually going to intersect at, though. So now what we have to do for this curve, because we don't exactly know where these points are at, we need to set this curve equal to each other. So we are going to get 2x is equal to x squared minus 4x. Solving now, or trying to get 0 on one side, we get x squared minus 6x. We can factor an x, so we get x minus 6 times by x. So we get the answers of x is equal to 0 or positive 6. Alright, so now what we have to do is we have to take the definite integral from, well, the top curve in this case is going to be 2x. So we get 2x minus x squared, plus 4x dx. Now, it's always of your own benefit to do algebra first. So we are now going to be taking the integral of from 0 to 6 of negative x squared plus 6x dx. Integrating this now, we get negative x cubed over 3 plus 3x squared, evaluated from 0 to 6. Alright, now time for the very scary part, the arithmetic. So we will get negative 6 cubed divided by 3 plus 3 times by 6 squared minus 0 divided by 3, negative 0 divided by 3 plus 3 times by 0 squared. So this is really just 0, so I'm just going to cross it out. But what is negative 6 cubed? Well, that is going to be the same thing as negative 216 divided by 3. Which, if I do my math right, that's going to give me 72. Negative 72. Alright, yeah, negative 72. Well, 3 times by 36, that's going to be the same thing as 3 times by 6, that's 18 plus, so 108. 72 minus 108 is actually just going to be 36. And I believe that would be our answer. So, another thing we can do, and in fact this is actually kind of interesting thing we haven't really gone over yet, is sometimes we have functions defined for y, like for example, x is equal to y squared. Well, in these cases, we have to have a different way for evaluating the area. Just kidding, it's really the exact same. So really, we're just adding up the same rectangles, but instead of doing a change in x, it's just a change in y. So it's really just the integral from a to b of f of y, which is the one furthest from the y-axis, minus g of y dy. Alright. Now we want to find the... So, now we want to use this to find the area bound by the following curves. So, we have x... So we have x is equal to 2y squared, and x is equal to 4 plus y squared. So we start by setting these curves equal to each other so we can find the zeros. So 2y squared is equal to 4 plus y squared. So now we just have to subtract this over, so we get 4 minus y squared is equal to 0. Solving for 0, we get negative y squared is equal to negative 4. So y squared, or let's just say y needs to be equal to plus or minus 2. So we're really just going to be taking the integral here from negative 2 to 2. Negative 2 to 2. Okay. Now, which one of these curves is going to be on the top, you might ask? And the answer is going to probably be this 4 plus y squared. So we'll say 4 plus y squared minus 2y squared dy. Getting the integral from 2 to negative 2 of 4 minus y squared dy. This evaluates to 4x minus y cubed divided by 3. Evaluated from 2 to negative 2. Alright. Well, evaluating this value at 2, we will get 8 minus 2 cubed is 8, so we're going to get 8 thirds minus, alright, so we're now going to get negative 8, because 4 times by negative 2, plus negative 2 cubed, which is going to be negative 8, but it's actually going to be plus, and then divide by 3. This here is going to evaluate to, well, this is going to become a positive 8, so it's going to become 16. And then, because we have this plus, this is going to be minus 16 thirds. So, now we can, let's see, so this would be the same thing as 5. So, let's see, this would be 10.66. Alrighty, now for the second equation, and that's... oh, never mind, that does work. Okay. So, for this one, we want to say y minus y squared, and we want to just set these equations as equal to each other, is equal to y squared minus 1. Well, what we have to do is we're going to get the y squareds on one side, so we get negative 2y squared is equal to negative 2. The negative 2's will cancel, so we get y squared is equal to plus or minus 1. So now we just have to integrate from negative 1 to 1. Alright, which one of these functions is going to be on top, you might ask. Well, let's set y equal to 0, and we'll see that this left equation is going to be on top. So we get 1 minus y squared minus y squared plus 1 dy. Simplifying this first, we get 2 minus 2y squared dy. And now it's just as simple as integrating this. So we get 2x minus, or sorry, 2y. What if I said 2x accidentally previously, but I don't care. Minus 2/3 of y cubed, evaluated at 1 and negative 1. Plugging in the value of 1, we get 2 times by 1 minus 2/3. Evaluating it at negative 1, we get, I don't know why I did an integral symbol. We get negative 2. Alright. Minus, oh sorry, plus in this case, 2/3. Okay. So we get 2 minus 2/3, so we get 4. Negative 2 minus another 4/3 is going to be negative 4/3. So this is going to become 2.3, or 2.66, I want to say. Repeating. Alrighty, well, that's all I have for you today. I hope this video has been informative, and hope you all have enjoyed. Goodbye.